All right, our first topic in this course that is genuinely new is I want to start by talking about what are called separable equations. And these are differential equations that can be separated in a certain sense. So these are things like y prime equals y squared. And so this is a separable equation that we'll talk about. And let's actually start by looking at this. I'm not going to make it a initial value problem. So that means that we'll have a general constant in our answer. But I could give you the general constant and then we could figure out what to do from there. But this is it. So I want to figure out what's the function whose derivative is equal to the square of itself. And so that's what I want to think about. Perhaps you can come up with a solution right away, or at least one of, not the whole family of solutions necessarily, but maybe you can come up with a solution right away. But let's pretend that we cannot. In separable equations, what we're going to do is we're still thinking of y as being a function of x. So I can write y as either y or y of x or f of x. And if I want to, I can think of y prime as being f prime of x, or in this case, when we're talking about separable equations, Leibniz notation is better. So we'll write it as dy dx. And so that's going to be our first step. Okay, so these problems will typically say solve the equation. That means figure out what are the solutions y, what are all the functions satisfying that differential equation. So y prime we're going to write as dy dx. Y squared is just y squared. And then these separable differential equations are the equations that we can separate variables, meaning that we can get all the y's on one side, all the x's on the other side. And so that's what we'll do next, is we're going to end up with 1 over y squared dy equals dx. Now I'm cheating. I want to mention that this dy dx is not a fraction. But in a lot of ways, it behaves like a fraction, and this is one of the ways where it behaves like a fraction, right? dy dx is just the derivative. It's the limit of the, so remember that y prime is the limit as h goes to 0 of a certain difference quotient, okay? And so it's not a fraction, but in a lot of ways behaves like a fraction. It's a limit of fractions, but that does not make it a fraction. Nonetheless, we can still get away with this here, and I'll explain why in the next step. So the reason why we can do this the reason why we would want to do this is that now we can integrate both sides. So what I've written right here is 1 over y squared dy equals dx is, technically speaking, nonsense. It doesn't make any sense to talk about dy or dx by themselves necessarily, unless you think of them as differentials, which is why we can kind of get away with this. But what we're allowed to do is we can integrate both sides, and now it's a completely okay equation. So now it's true that 1 over y squared dy, the integral of that, is equal to the integral of 1 dx, or just the integral of dx. And so now we're allowed to integrate both sides, and the integral of 1 over y squared would be negative 1 over y. The integral of 1 dx would be x, and we need a plus c somewhere. Doesn't matter if you put it on the left or the right, you can just always move it to the right because it's a general constant anyways. And now the name of the game is to solve for y. So the first thing that we're going to do is we're going to multiply both sides by minus 1. And we end up with 1 over y is equal to negative x. Now c does not stand for any specific number. So negative c and c are the same thing because they're just generic constants. You don't have to change the sign there. You can if you really want to. And then finally, we'll solve for y by inverting both sides. So y is going to be 1 over c minus x. And it turns out that these functions, 1 over a constant minus x, are exactly the functions such that when you differentiate them, you square them. So maybe right away you saw that negative 1 over x was a solution, because negative 1 over x, when you differentiate it, you end up with 1 over x squared. And that's the same as this function, negative 1 over x quantity squared. So this is a function whose square is equal to its derivative. Okay, and in fact, these are all the functions whose squares are equal to the derivative. Now, I should say just one more word about separating variables. The real reason why this works is because of the role of differentials. So dy, if we were to think of, if we have y equals f of x, then dy is f prime of x dx. In other words, dy dx. I should write it a little bit better. Dy is the derivative times dx. And this is really what we're doing when we separate variables. When I write that we have dy, really what we're doing is we're kind of thinking of dy as dy dx times dx. Okay, and so in a way it behaves like a fraction. You can think of it kind of like a fraction where the denominator cancels. But really what's going on is that we're thinking of these as differentials. And that's what really saves the day. But nonetheless, however you want to think about it, this trick works. This is called separating variables, and this is kind of our first step of equations that we couldn't solve yesterday, okay, or equations that we couldn't do in Calc 1.